In this video, we're going to go through some revision notes for Physics 0625 Cambridge IGCSE for topic 10 about thermal expansion in solids, liquids, and gases. So let's begin. To begin with, we're going to first define thermal expansion, and then we're going to go through thermal expansion and some examples of thermal expansions in solid, liquids, and gases. So, thermal expansion. Thermal expansion is the increase in volume of a material when its temperature rises. So as we know, every material or every object has mass and volume, or anything in matter has mass and volume, because matter is equal to mass over volume, right? So thermal expansion is when the volume of an object increases, the space an object takes up. That space increases due to an increase in temperature. So as you're increasing the temperature of an object, you're adding more heat to the object, its volume is increasing, the space it takes up is increasing. How does this happen? Because when heated, molecules move around or vibrate faster, causing to knock each other and push each other apart. So when a material is heated, the molecules or particles or atoms inside the substance or objects begin to vibrate faster. They increase their kinetic energy. The kinetic energy increases. They begin to vibrate faster, move faster. Because of this, there's a lot of collisions between each other. As these collisions occur between each other, particles are colliding with each other more, and due to this, the surface area of the particles is being increased because each particle, due to collision, is pushing each other away. It's the intermolecular space taken up by the molecules that increases, but the molecules themselves remain the same size. Yes, so as we're increasing the temperature, as we're heating the molecules or particles, the particles are moving faster and they're bumping into each other continuously. This is why they're pushing each other apart and increasing the volume. But this pushing apart is only changing the intermolecular space between the particles, but the molecules remain the same size. The intermolecular space is just altered due to the molecules pushing each other apart continuously. So now that we know what thermal expansion is and we've got an idea about that, let's have an intro on thermal expansion in the terms of particles. We have solid, liquids, and gases. So if we increase the temperature, by expansion here we mean increasing the temperature at constant pressure. So keeping the pressure constant, but increasing the temperature in solids, liquids, and gases. If you increase the temperature at constant pressure inside a solid, it's going to expand slightly because low energy molecules cannot overcome the intermolecular forces of attraction holding them together. So solids are going to expand the least simply because the molecules or particles in solids are very tightly packed to each other. Liquids, on the other hand, are going to expand a bit more than solids. They are not as much as gases, but they're not as less as solids. They're somewhere in between because molecules have enough energy to partially overcome intermolecular forces of attraction holding them together. Here, partially. So liquids is just a little bit more than solids. They expand a bit more because, again, liquids and gases are fluids. They have the ability to flow, so their particles are able to slide past each other. This is why the intermolecular forces of attraction are not as strong as the solid. Gases expand significantly. They expand the most because high energy molecules have enough energy to completely overcome intermolecular forces of attraction holding them together. So imagine gases are already the highest energy particles. The particles in gases are moving continuously at a very fast speed. So they already have so much energy. Now imagine you're adding more heat to the particles, you're adding more temperature to the particles. The gases, the heat in the gas, the heat added to the gas is just going to add more energy to these particles. And this overload of energy will within a very small period of time is going to break almost break the intermolecular forces of attraction. This will cause it to expand the most. So again, solid, liquids, and gases in expansion. Solids expand least because of the large number of intermolecular forces holding them together very tightly. Liquids don't expand as much as gases, but they expand somewhere in between because the intermolecular forces are somewhat broken, but not completely because particles are sliding past each other. And gases expand the most because they are already at high energy particles, but we're going to add even more high energy to the particles. This will cause the intermolecular forces to break very easily and expand the most. This is an example of gas expansion. So if we look at the illustration here, in the first one, the gas is cold and the particles are pressed weakly on the piston. So the piston, now when heated, particles are more faster to push with greater force on the piston upwards, and the gas is expanded at constant pressure. So we have a container here, we have a piston, and the piston is not altered, so we're not touching the piston, okay? But we're just going to play with the gas molecules here. The gas molecules here are cold, okay? This is why they're pressing very weakly on the piston. As you can see, the arrow is very small. This means their force is very small from one gas particle to the other. Or the gas particles, they're actually in Brownian motion. The Brownian motion here is very slow. Compared to the Brownian motion here, if you look at the arrow, it's much longer because in this one we heat the particles. Because we heat the particles, their Brownian motion increases and they are pushing each other with a greater force. Due to this greater force, they start pushing the piston up because they're colliding with a greater force, and this shows that increasing the temperature expands the gas. Consequences of solid expansion. So we have, in the syllabus, we have 3 consequences of solid expansion: metal railway tracks, road surfaces, and bridges. Why? Because on hot days, where there is a lot of heat supplied, it's a danger that they might bend. So these are daily used surfaces all around us, and on hot days, especially in places where it's very hot and there's a really high temperature, there's a big danger that these surfaces might bend and cause danger to the environment. Uses of expansion. So the first use of expansion we're going to study is a bimetallic strip. This is a strip made of 2 metals joined firmly together, where one metal expands much more than the other. So it's a strip. It's a strip. Okay, it's a strip. It has 2 metals, one up, one down. The 2 metals are chosen in such a manner that one metal will always expand much more than the other. So these are 2 metals. As the metal expands, the metal starts to bend. Okay. Now, if the metal that's up is a better conductor of heat than the metal that's below, is going to bend downwards like this. Okay. As strip is heated, the metal expands, causing the strip to bend. Exactly. We have 2 metals. When the strip is heated, one of the metals is going to bend. The metal that bends more is always on the outside of the curve, because the outer curve is the longer than inner strips, and it's used in devices like fire alarms, thermostats, and temperature activated switches. Usually in automated or automatic switches, these are used. So whenever we need to let's say turn on or off any switch, we usually apply heat to it, or there's a heat supplier that's already connected to the bimetallic strip, and that heat supplier supplies heat to the bimetallic strip automatically, and the bimetallic strip bends to switch on and off the switch. The second use of expansion is a rivet. This is a material that is, when cooled, it contracts and pulls 2 metal plates together tightly. So this is a hot rivet. The rivet is actually made as such a material that it contracts whenever it's cooled. That's how the material is made. So as you can see here, this is a hot rivet. The layers are not touching each other. But a cooled rivet, both of them have contracted and they've pulled against each other, and the layers are touching each other. Other 2 common uses of expansion are thermometers and metal lid on a glass jar. Thermometers, I think we all know, they use expansion of liquids to measure the temperature, usually in thermometers that use mercury. As for metal lids on a glass jar, when you have a glass jar and you have a metal lid on top and it's really difficult to open, so usually heating this lid is going to cause expansion in the particles of the solid and make it easier to open the lid. This is a very daily life example. So with that, we have finished everything about, or mostly everything about thermal expansion. Thermal expansion is solid, liquid, and gases, and some consequences and common uses of thermal expansion. Now, jumping to internal energy. Internal energy is the total energy stored inside a system by particles that make it up. due to their motion and positions. So it's the total energy. The total energy, not because a particle, again, not a particle, an object has many energies. It has kinetic energy, it has gravitational potential energy, it has potential energy, it has thermal energy. But internal energy is the total energy stored inside an object due to their motion and positions. The key words here are motion and positions, because if this is the energy due to the motion and positions, this means motion we're referring to kinetic energy, and position we're referring to potential energy. So this means internal energy is kinetic energy plus potential energy. So it's the total energy inside the system due to an object's kinetic energy and potential energy. Temperature increases the object's kinetic energy and internal energy. Both are directly proportional. What happens when heat is applied to an object? So when heat is applied to an object, the temperature increases. This will increase the kinetic energy of particles, and since kinetic energy of particles is directly correlated with the internal energy is also going to increase. And if the internal energy or total energy of the system increases, it's going to change the state of an object by either breaking the bonds or increasing the potential energy at a constant temperature. Gases and heat. So this is a normal gas at low temperature, and this one is a heated gas at high temperature. At low temperature, the gases are free to move and have no intermolecular forces, while a heated gas, the gas moves much faster with a much higher kinetic energy. Fixed points of water. So for the points of water, we have pure ice and pure water. Pure ice melts at 0 degrees Celsius, and pure water boils at 100 degrees Celsius at atmospheric pressure. So we have fixed points of water. 0 degrees Celsius and 100 degrees Celsius. 0 degrees is where pure ice melts, 100 degrees is where ice boils. Now, a quick, very important note is that during changes of state we have, and the thermal changes of state we have generally is melting, boiling, freezing, condensation, sublimation, and solidifying. Okay, during all these states, the point at which the state begins, so for example you're melting an ice cube, the point where the object reaches its melting point, or the point where an object reaches its boiling point. Okay, the point where the state change begins to occur, at that point there is no change in temperature. The temperature is always going to be constant because all the energy during the change of state is being used to break the bonds, either to bring them away from each other to form solid to liquid to gas, or to bring them closer to each other to form gas to liquid to solid. So the temperature during the change of state is always going to be constant. Now let's have a brief about a few of these states. First, condensation and solidification. During condensation, particles lose kinetic energy and move more slowly. They become closer together until they don't have enough energy to overcome intermolecular forces of attraction between molecules. They only have enough energy to flow. Solidification is the same process, but by the end, particles have only enough energy to vibrate in position. Again, the whole process occurs without temperature change. Temperature stays constant. Condensation is simply particles are losing kinetic energy and becoming slower. So particles moving very fast. They're becoming slower. Eventually, they've lost all the kinetic energy, so they only have enough kinetic energy to just keep moving very slowly and just flowing across one another. Solidification is continuing of condensation. Okay, particles are moving slowly. Over time, they just keep continuing to lose kinetic energy, and they just become, they stop flowing and they just stay in their position, just begin to vibrate. That's how much kinetic energy they lose. So it's just a process of particles losing kinetic energy and becoming slower and closer to each other. Boiling and melting, on the other hand, is somewhat the opposite of those. Condensation, solidification. Boiling is when liquid water is heated by adding thermal energy, and the temperature of water rises till it boils. At the boiling point, again, water does not get any hotter because internal energy is not increasing. We said this because the temperature does not increase. Additional thermal energy goes into overcoming the intermolecular forces between the water molecules. Melting is when the solid ice is heated by adding thermal energy from the surroundings. At melting point, the thermal energy is added, but the solid water does not get any hotter, like we said, because the temperature does not change. So boiling is when we have a liquid, and the liquid is heated by adding thermal energy, and this increases the temperature and of the water until it reaches boiling point and starts to boil. During this point, again, there is no temperature change. It's just the distance between the particles is changing. Melting is when you have solid ice and you add thermal energy to solid ice from the surroundings, causing it to melt. The last part we're going to cover is heating and cooling graphs. So heating is when energy is transferred to the system and kinetic energy of the molecules increases. Cooling is when energy is transferred away from the system, is dissipated to the surroundings, and the kinetic energy of the molecules decreases. So heating is we're transferring energy to the system. We have a system, we're putting energy into it, we're putting energy into it to increase its temperature. Cooling, we have a system and we're taking away energy, we're taking away energy to decrease its temperature. We're going to study this one in a much more detailed curve here, heating and cooling curves. So on the y-axis, we have temperature against Celsius. On the x-axis, we have heat added, the amount of heat, or you can say delta H. So looking at it from down to up, the state is solid. From solid, we add energy, we add heat, then melting begins. This is the melting point. Melting begins at this point, and it transfers from solid to liquid. By the time melting point is reached and it becomes a liquid, then we add more energy until vaporization begins. During vaporization or evaporation, the liquid becomes gas, and during this point, again, there is no temperature change because, as you see, during the melting point and during the evaporation, the temperature remains constant because, like I said, all the energy is being used to move the particles away from each other. And after it's become gas, you can increase the temperature and it's just going to expand. Now, looking at it from top to bottom, we have a gas here, and we're going to remove energy from the gas, causing the particles to slow down more, remove its kinetic energy. Condensation will begin. During this point, again, temperature is going to be constant because all the energy is being used to bring the particles closer to each other. Now we're going to take away more kinetic energy all the way down to here. The particles are going to become liquid and then eventually form a solid because we're just going to keep taking away kinetic energy for particles to become slower and just come right next to each other and form a solid and just vibrate with each other. So that was the cooling and heating curve altogether. This is the cooling and heating curve separately. This is the heating curve. We have solid, melting, temperature is constant, melting point. Then we have liquid. There's the boiling point, temperature is constant. Increase the temperature and expands into a gas. Cooling curve is just flip the heating curve. It's just the opposite. These are some factors that are affecting a rise in temperature. The mass of the substance, it is inversely proportional. So the greater the mass of the substance, the less the rise in temperature. The amount of thermal energy supplied directly proportional. Of course, if you supply more thermal energy, or if you just supply more energy to an object, by default, the temperature of the object will increase. Type of material. Of course, not all materials increase their temperature by the same rate. Some materials will increase their temperature faster if you apply the same amount of thermal energy compared to any other substance. For example, copper and magnesium. If we apply 5 degrees Celsius of thermal energy into both copper and magnesium, they both will not increase by the same rate. So type of material is very important. And the most important from all of these is specific heat capacity of the substance by symbol C. So specific heat capacity, what is this? This is the amount of energy required to raise the temperature of a unit mass of a substance by 1 degree Celsius. By unit, we mean 1 kilogram mass. So we have a substance and we want to increase its temperature unit mass by 1 degree Celsius. So we have to input a specific amount of energy to do this. This amount of energy that we need to raise the temperature of a unit mass by 1 degree Celsius is the specific heat capacity. Two very important rules of specific heat capacity. If a substance has low specific heat capacity, it heats up and cools down very quickly because it takes less energy to change its temperature. Why? Because we said amount of energy to raise the temperature by 1 degree Celsius. If it has low specific heat capacity, it means the amount of energy is not so much. So you can easily heat it up or cool it down. But if it has a high specific heat capacity, for sure it will take a lot of time to heat the substance up and cool it down because the substance requires a lot of energy for it to increase or decrease by 1 degree Celsius. This is an example. We have a copper block, aluminum block, and water. Specific heat capacity of water is 4200 joule per kilogram degrees Celsius. Aluminum is 910 joule per kilogram degrees Celsius, and copper is 390 joule per kilogram degrees Celsius. From all of these, the highest one is for aluminum. No, the highest one is for water. This means water has the high specific heat capacity and is going to take the highest time to cool up or cool down or heat up. While copper is the opposite. It has the least specific heat capacity, so it's going to take the least amount of time to cool down or heat up, and aluminum is somewhere in between. To calculate specific heat capacity, we have a very nice formula here. Specific heat capacity is equal to the energy required divided by the mass and temperature change. So we're just technically combining all the factors that we took up here, factors that affect the rise in temperature. Because in the end, specific heat capacity is the amount of energy required to produce a rise in temperature. So we're going to use the factors that affect this rise of temperature to calculate the specific heat capacity. So specific heat capacity by symbols, C is equal to E over M times delta T, change in temperature. To calculate E is mass times specific heat capacity times change in temperature, and change in temperature is energy divided by mass times specific heat capacity. The unit of specific heat capacity is joule per kilogram degrees Celsius or joules per gram degrees Celsius. That was specific heat capacity. So heat capacity, but of a specific amount or a specific substance. This is heat capacity in general. Heat capacity in general is just the energy required to raise the temperature of any substance by 1 degree Celsius. Specific heat capacity is to raise the temperature of a unit mass 1 kilogram by 1 degree Celsius. Heat capacity is any substance just by 1 degree Celsius. Unit is joule per degrees Celsius, not kilogram or gram because we don't have a unit mass. The formula is energy divided by delta T or mass times specific heat capacity. And with that, we have finished the chapter. Now we're just going to go through some practice questions to review specific heat capacity. The first one is this one. A 50-watt electric heater is used to heat a liquid of specific heat capacity 2.4 joule per kilogram degrees Celsius. What's the time needed to heat 50 grams of liquid from 20 to 120 degrees Celsius? So what do we know? We know 50 watt is the power. We know C is the specific heat capacity. We know the mass. And we know the delta T, change in temperature. So first, we're going to calculate the energy. The energy by the formula, we're going to multiply 50 times 2.4 times 100 to get 1200, okay? Now that we have 1200, we're going to use the formula of power because they gave us power, right? So we're going to use the formula power. Power is energy divided by time. We know what's power. We know what's energy. We need to find time. So rearrange the formula for time. Time is equal to energy divided by power. And substitute the values. Energy is 1200. Power is 50. 1200 divided by 50 is 240 seconds. Next question. What's the heat removed from 5.2 kilogram of water to change its temperature from 60 to 54 degrees Celsius when C is 4200 joule per kilogram degrees Celsius? What is it given? We know the change in temperature, 54 and 60. We know the mass and we know the specific heat capacity. What do they need? They need heat. Heat, by heat we mean the energy here. And the formula is E is equal to M times heat times delta T. So we're just going to use this formula and substitute the given values. To find delta T, temperature from 60 to 54, final minus initial is negative 6 degrees Celsius. So 5.2 times 4200 times negative 6 will give us negative 13,1040 joules. And this is the heat removed from 5.2 kilogram to change its temperature from this to this. Next question. A substance of specific heat capacity, this much, with temperature of 25 degrees Celsius and mass of 0.71 kilogram, what will happen to its temperature if it's supplied with 100 joules of heat? So again, they're asking us a question about temperature and heat. So by the formula, we know the temperature, we know the formula for this, E is equal to M times T times delta T, and we need to find delta T. So substitute the values. They have given us energy, which is 1000. They give us mass, which is 0.71. They give us C, which is 820. Multiply all of them and isolate delta T. You're going to find delta T is 1.7 degrees Celsius. Now that we have found delta T is 1.7, delta T is temperature of the final minus temperature of the initial. Delta T is 1.7 and the initial temperature is 25. So 1.7 is equal to TF minus 25. Move 25 to the other side. Isolate TF, and TF is equal to 26.7 degrees Celsius. Okay, this is the last question for this chapter. 2 kilograms of water with a specific heat capacity of 4200 joule per kilogram degrees Celsius is at 20 degrees Celsius and added to 5 kilograms of metal at 120 degrees Celsius with a specific capacity of 660 joule per kilogram degrees Celsius. What is the final temperature of both the water and the metal? So here, the metal is losing heat and the water is gaining heat. So the heat lost by the metal, let's call this negative energy of the metal. And the heat gained by the water, let's call this positive heat of the water. Okay? Now the energy formula is, we know, mass times C times delta T. So let's apply the formula in both equations. Negative, we keep the negative outside. Mass times C times delta T of the metal. And we're just going to expand energy into the formula, okay? Keep the positive outside. Mass times C times delta T of the water. Now substitute the given values. We know mass is 5, C is 660, and we don't know the initial, but we don't know the final, but we know the initial minus 120. Here again, mass 2, 4 to 200. We don't know the final, but we know the initial minus 20. So substitute all the values and distribute positive inside here, distribute negative inside here. And now just solve for T. Isolate T, use linear equation methods, isolate T and solve for T. You're going to find that T is 48.2 degrees Celsius.